Dear friends, today I'll explain to you the difference and the difference between BJT and FET, as well as the working of field effect transistor before going to construction and working of FET. Let's we differentiate first of all BJT and FET. BJT means bipolar junction transistor. Current is because of both electrons as well as the holes. Here it is a FET. Current will be only due to either electron or the holes. Now in BJT, there is a emitter terminal, base terminal, and the collector terminal. Base controls the current between emitter and collector. So that's why it is called current controlled device. Current controlled device because collector current is always a function of the base current. On the other hand, FET, here there is an emitter in BJT, here it is a source. In BJT it is a base, in FET it is a gate. In BJT it is a collector, in case of FET it is a drain. Now here the gate controls, but this is not the current control device, this is the voltage control device because the drain current is a function of gate source voltage. The voltage applies between the gate and the source. So ID is a function of what? ID is a function of VGS. Here IC is a function of the base current. This is the basic difference between. Now the next question is, we were having BJT, then why FET? What is its purpose? Actually, FET is a very good device over BJT because the most important characteristics of the FET is the very high input impedance. Impedance means resistance, basically, mean ohm. Is very high input impedance over the BJT. That's why FET becomes a special. Now FET, FET includes JFET, Junction field effect transistor, and second metal oxide semiconductor field effect transistor. Okay. Then MOSFET further classified as into the two classes: depletion type, depletion mode, and enhancement mode, enhancement type. MOSFET again into the two classes. MOSFET transistor has become this one. The MOSFET transistor has become one of the most important devices used in the design and the construction of integrated circuits, ICs. So basically, in IC, the MOSFET is generally used, okay, because of its special characteristics. Now we coming the construction part. Structure of FET. Now this is FET, N-channel FET. There are two types of again. FET may be N-type or maybe P-type. Here I am going to explain the structure of N-type. Now this whole chip, this is N-type. N-type material that forms this N-type material forms the channel between embedded layers of the P-type material. So this is P-type material. N-type material, it forms a channel, between embedded types of the P-type material. The two P-type materials, this one and this one, it is connected together like this, and to the connected together and then to the gate terminal. So they act as a P-type act as a gate. Now this is the figure, this is a structure when there is no applied voltage. No applied voltage. This is very important. No applied potential. So there is a P, there is an N. So what happened? P-N junction. There are two P-N junction, this one and this one, under no bias condition. And results the depletion region. So this is the shaded portion. It is basically depletion region. This one. Depletion means depleted. Means there is no carrier there is no charge carrier. No carrier available here to move. That's called the depletion region because of the combination of P and N. Depletion is that region void of the free carriers. And the depletion regions are symmetrical because no applied voltage. They are symmetrical so long as there is no biasing. So source terminal, drain terminal and the gate. Now you can compare the FET, the working of FET with the flow of water. So this is a source from where the water is coming, and to make the water flow there is a need of pressure difference. More the pressure difference, more there will be the water. Similarly, between source and drain, there will be current, electron current. There will be more electron current if there is more potential difference between source and drain. Because there is a source of electron. S means source of electrons. For electrons to move, positive potential is required here. Stronger the positive potential, more there will be current. So more the pressure difference, more will be the water. The water is going to drain here. Similarly, electrons, the source of electrons, reaching here, so this is the drain. So between source of water and drain, there is a control called the gate. So you can have more or less water, by changing this knob. Similarly, there is a gate. By giving a potential to the gate, negative potential, okay, the current can be controlled, which is flowing between source and drain. So for water flow, pressure difference is required. This knob controls the water, amount of water. Similarly, potential difference makes a current to flow. That current is controlled by the gate. Now when here in this diagram, there is a source, the drain, a potential difference V double D is applied between source and drain. Source is actually at the earth potential. So if this is of 10 volt battery, so 0 will be here and plus 10 will be at here. So electron current will flow from source to drain. So this is a gate terminal. The gate is connected to the earth potential, mean gate is at 0. The gate is at 0, the current is flowing source to drain. One thing you notice that the PN junction is now not symmetrical, it is asymmetrical. Asymmetrical means more wider here as compared to this place, is more wider near the drain end as compared to the source end. Now the question is, why it is more wider towards the drain? The conventional current, which is ID. As the electron they are moving from source to drain, the conventional current will be along this direction. It will be along this side. So this is the direction of the conventional current, opposite to the electron current. When there is no gate potential and as the current is flowing from source to drain, as the electron they are moving from source to drain, that is conventional current, drain to source, okay, the depletion region is wider, it is more wider towards the drain end as compared to the source end. The question is why? The answer is very simple. Actually the N channel behaves as a resistor. Okay, so this point is at the ground potential, mean this end, this ground potential. Now positive potential is applied at here, let it is 10 volt. So if it is 10 volt, here will be 8 volt, here will be 6 volt, here 4, here 2, like that. So a potential is established and it is increasing going from source to drain and more in magnitude towards the drain end. Now just see, the potential is positive and this is a N channel. If it is N and a positive voltage is applied to N, what happen? Reverse biasing with respect to P. So this is N, this is P, and because of this potential which is more positive towards the drain, more positive potential towards the drain makes a reverse biasing to an PN junction, but reverse biasing will not be uniform from here to here. Reverse biasing is actually increasing towards the drain end. From source to drain it is increasing. There is more reverse biasing going from source to drain because of this establishment of the potential as a result of the flow of drain current. So that's why this is more wider towards the drain and less towards the source, like this. Along this side it is a source drain voltage. Along this side it is the drain current. When we go on increasing this battery voltage, what happened? The current go on increasing. There's a linear increase up to this point. That means the inverse of the slope is a resistance. Okay, and because it's a constant slope, mean resistance is constant. N channel offers a constant resistance till up to this voltage. Beyond this voltage, what happen? The slope is decreasing. Okay, and because inverse of the slope is resistance, that means now the N channel offers more and more resistance because there is more reverse biasing increasing towards the drain end with increasing this voltage because more and more reverse biasing established towards the drain end. So as the resistance is increasing, the slope is becoming lesser and lesser. So at this point, this is called pinch of voltage. After pinch of voltage, there is a constant current. Current cannot increase further. That means the N channel is giving almost infinite resistance to the current. So that's why current cannot increase further. So it becomes constant. So after this is called pinch of voltage. After pinch of voltage, the current is constant. Okay. So FET behaves as a constant current source because the current becomes independent of this voltage. And this current is known as ID, S and S. Okay. Mean when the gate is shorted, this S mean shorted gate. Gate is at earth potential. And the current is drained to source, conventional current. Okay. And current becomes constant. It cannot increase further because the pinching of the depletion region, because the width, the channel between the two depletion region is too narrow, so current cannot increase further. So pinch off doesn't mean that current drops to zero. Pinch off means the current becomes constant after a certain voltage. That is called pinch off. Don't confuse that. Pinch off means that current reduced to zero. No. After pinch off, the current becomes constant. Now, if we repeat this experiment, okay, with the different, by giving some gate voltage and giving gate voltage, negative gate voltage to P. Negative gate voltage to P mean by making it reverse biased from the outside also. It is already reverse biased when the gate was at the earth potential. Even then there was reverse biasing here, more reverse biasing here as compared to this point. But when the negative biasing is applied from outside and we repeat the experiment, then we got the second curve, this one. So this curve is at -1 volt reverse biasing. Gate is at -1 reverse biasing. So what happened? This curve is similar to this, but the saturation current drops down from this value to this value. And secondly, pinch off started at firstly when there was no gate, the pinch off voltage was here. Now it comes to this point. The at the less drain source voltage. Okay, pinch off voltage becomes the channel is pinched off at lesser drain source voltage. Now, if the gate source voltage is further increased, even again the saturation current drops to this value and pinch of voltage is still further reduced. Okay, now just more making it more reverse biased, the saturation current drops to this value very near to 0 and pinch of voltage is where it is also very close to 0. That means now the FET turns off. There will be no current beyond this gate source voltage. So this is the gate source voltage which is giving some saturation current. By increasing further, there will be no current. So the pinch of voltage is almost here. It is very close to 0. The locus of pinch off values. Okay. Dear friends, this is the animation. Dear friends, this is the animation showing the working of junction field effect transistor. This is the source, this is the drain, and this is our PN junction. Okay, this is P sorry. This is a P-type layer. This is a P-type layer, and this white portion is a depletion region connecting both the P-type. It becomes a gate. Now potential is applied between gate and source. This is a source, this is a gate, and this is a potential VGS. And because this is a P terminal, we can increase VGS. VGS can be increased from 0 to minus 2.5. Already we are giving a negative potential to P, mean the gate is becoming more and more reverse biased. Mean the gate will close. That mean the gate can be closed by giving more and more negative VGS. Okay. Second, at any gate source voltage, at any mean, the voltage may be -1, maybe minus 1.5. Then the current which is flowing from source to drain can be a function of the source drain voltage, which is positive at this end and negative at this end. This end may be at the ground potential. So this is a drain source voltage. Okay. Here we are giving 0 to 10 volt or 0 to 9 volt between drain and source. So we can vary this drain source voltage by changing this knob, and we can make the VGS variable by changing this knob. And here is a graph between drain source voltage and the drain current. Okay, so here it is a ohmic region. After that, from here the pinch off. This is pinch off voltage. After then, the current becomes constant. Now I'm going to switch on the animation. I'm going to on the animation. You just see how the gate current will be affected. So just see how the drain current will be affected. how the drain current will be affected by changing the gate source voltage or by changing the drain source voltage. Look carefully how the drain current is a function of this and this. Keep in mind, making more gate source voltage mean making it more reverse biased. The closed gate will closed more and more with more and more VGS. Second, VDS can make the drain current. VDS can increase the drain current, but up to a certain limit. After then, there is a saturation region. After pinch off, there is a saturation. This how the VDS it affects the drain current. Okay, so keeping these things in mind, just see how the animation is.